Okay, I'm going to solve that problem in the next hour and a half. Wow. Okay, thank you, Jim. That's if. Yeah, thanks. Yeah, at least I can get under it really easily. Okay, so that I'm sorry, I'm a little thrown by that introduction. It's a real pleasure to come do this. I'm always grateful when Jim invites me over to do this. Having the Duke Network Analysis Center here is like one of the best parts of my professional life in the Triangle. So it's pretty cool, even if it makes me wear a darker shade of blue every once in a while. So what we're going to try to do with the next hour and a half, or ballpark, is first a mix of some slides, which is sort of a background, and then a particular R notebook. Dana, am I supposed to give them instructions about running the core of anything, or no? Just she disappeared. I don't know. Okay. When we get to the R notebook, there are things that you might still need to install to make it work. At the top, there are definitely things that you will not be able to run today when we're there doing it at the bottom, unless you've like souped up your system in a way that mine was not souped up until about yesterday afternoon around 3 o'clock. So, but we'll get there. So that will all be at the end. So we'll start with PowerPoint, then we'll finish the end of the talk in our notebook. Basically, what I want to try to do is I want to try to explain both sort of colloquially and theoretically what do I mean when we use these words community detection, in particular in a social network analysis or network science context, and motivate the entire thinking about this around some examples about why it might actually be useful to think about your data this way. We'll talk about one particular block of ways of calculating communities. This is an enormous field where they're by no means going to cover everything there, but we'll give you some links to some software. And if you get sort of nothing else out of my babbling at you with these slides, it will be you will learn the words resolution parameters, and you will decide that they are important, hopefully. There are some slides, which is a very, very too short introduction to what are called multilayer networks. We will undoubtedly not talk about part 3 because I will be disastrously running out of time at that point and want to jump to number 4, which is just demoing some of these things in our notebook. None of this would have happened without some great collaborators over the years that I've had the pleasure of learning from, who have really shaped my thinking about these kinds of problems, and whose work are referenced at some point or else in the slide here. They're grouped into loosely, have I spent most of my time working with them when they were faculty, postdocs, grad students, or even undergrads. Undergrads play a huge role in my research group, and in particular, I got into studying networks because of some work that I did with these 3 yellow-colored names back when I was junior faculty at Georgia Tech. The rest of the colors are obvious in the 2 shades of blue, albeit they don't. Some of these people have sadly moved on, like Skylar Cranmer is no longer associated with this shade of blue. He's now in political science at Ohio State. But great people, lots of funding from different agencies, font substitution problems going between a Mac and a PC, so this now overlaps in a way it did not before, but the apology here at the bottom that in this talk I will be grossly self-absorbed, motivated by my own work and my own experiences in thinking about these kinds of problems. But we'll try to give you pointers to some review articles, not all of which I wrote. And so you will have opportunity to see references to other people's ways of thinking about these problems, because certainly Jim is being overeager in calling me the world expert. It is certainly not a definitive article. I hope I am just an expert, but yeah, that's maybe even up to a debate in some corners. So here's sort of your outline of what we're going to try to do. The reality is that it's going to be ballpark, some theory, some examples, some demo, and lots of bad jokes. So probably these percentages are off. All right, so the philosophical disclaimer that backs all this up is actually got a little bit of the history of the Duke Network Analysis Center in it, which is that the second year that we all met together, where Jim pulled us all together, back in the days when we used to meet over in the Soch department around the conference table, there were so many more people at the first meeting of the second academic year that he thought, well, we better introduce ourselves to each other because we didn't know everybody around the table. And so, of course, Jim is accused, he will self-identify that he has been accused of turning everything into a network. I kind of take that one step further and say pretty much every data set I've ever played with, to me, is a network, and it's a graph partitioning problem. I'm, for whatever reason, obsessed with taking data and finding clusters or groups or whatever language that you want to use about how the network is structured. And the reason for this is because there's a duality often in any data set, but I feel like in particular in network data sets, between the structure of the network and the function loosely defined, where by function I mean either a mix of how did that network come into being, or what kinds of processes might run on that network. Certainly how a disease spreads through the network is intimately tied, as a for example, to the large-scale structure of the network. And so here, communities, as depicted in this sequence of images that I stole from some work of Aaron Clauset, demonstrates that this hairball here might be better visualized as being split up into 3 groups, each of which is internally has many connections and fewer connections relatively between the groups. And then there might even be some substructure inside of those where each of these groups, the blue group, sort of splits up into smaller groups, similar with the green and the red. And if you're a disease, you anthropomorphizing the disease, if you are a disease spreading on this network, right, it's really easy to spread around between tightly knit groups of individuals, and then you kind of have to get lucky to hop from one group to another group. And so those barriers between the groups, those jumps, those bridges, become key to understanding how quickly a disease or a piece of information or what have you will spread on this network. And so this understanding the structure gives us some insight into processes like this. Or sometimes it just simply helps us visualize it. Jim will do lots of visualization later this afternoon, or give us other intuitive understanding. So we'll start with the karate club. This is almost obligatory to start with the karate club. There's a few of you knowingly nodding with a smile on your face. Not too many of you look like you're going to tear your hair out yet. Okay, so who knows the story of the Zachary Karate Club? You can admit the few of you who nodded, or a few of you nodded, but many of you do not. Okay, so this is probably not truth. This is like actually go look at the paper, but this is sort of the urban myth version of Zachary's Karate Club. Zachary's Karate Club was a real university karate club, and Zachary was the lucky soul who, for whatever reason, I don't know why, decided to survey the individuals in this university karate club about their friendship links outside the club. And so the 34 nodes in this network diagram represent the 34 members of the club who were in the largest connected component, as defined by Zachary's surveying of whether or not people were friends with each other. And then this amazing thing happened, which was they got into a fight. Of course, it's a karate club, so it's like they get into a fight every day. But I mean, in addition to, it wasn't just like a cool Bruce Lee fight. It was an argument about the future direction of the club. And then the club split into 2 rival clubs. Now, if you put yourself in this situation, right, I'm not a sociologist. Anything I claim about what people do in the real world is probably wrong, since A, I'm not a sociologist, and B, being a mathematician makes me far from normal, right? You all know the joke, what's the difference between the introverted mathematician and the extroverted mathematician? The extroverted mathematician looks at your shoes when they're talking to you. So even me, as the person looking at your shoes, is going to think, well, all right, they had this argument, and if I really care about the substance of the argument, then that's probably going to influence what I do, because my old club doesn't exist anymore. It is now split into 2 rival clubs. Which club am I going to join? If I really had a dog in this fight, that might influence my decision. But if it doesn't, I'm going to ask my friends which club they're joining, and I'm probably going to go join the club that most of my friends went and joined. And for the most part, that appears to be what happened. There was a fight. The 2 rival clubs where the instructor and the president of the club went off, and the lead instructor and the president went off and joined, created these different clubs. But in this force-directed layout here, we've deliberately color-coded the nodes, black and white, closed, open, whatever you want to call it, into how the memberships worked out in the two rival clubs. And if you were to just look at this and think about different ways that you might try to partition these nodes into two different groups, almost any method you're going to come up with if you were forced to partition it into two different groups is going to split it pretty darn close to right here in the middle. This particular partition that I'm documenting here, which splits it up into 4 groups, because I've also sort of split up this group here, and I've made a cut right here. So there's this group, this group, this group, and this group happens to optimize a quantity that you will, if you don't already know something about, you will know too much about in the next hour and 15 minutes, called modularity, which measures the total weight of the within community edge weight relative to what you would expect in a random model. And we'll spend a lot of time talking about that, but that's just one way to cut this into 2. There are many other ways to cut this into 2. Virtually all reasonable ways to cut this into 2 split it this way, except for maybe one or the 2 people in the middle here, because there's some overlap. So much so that if your method does not nearly split this into 2, then in the infamous words of Eric Kalakshik, who's a statistician at BU, if your method doesn't work on this network, then go home. He sort of said this in a moment of peak at an opening workshop on a whole program year on networks that we had here at the Statistical and Applied Mathematical Sciences Institute in the Triangle, and he got sick of seeing so many of these these kinds of visualizations and people talking about community detection on this, that he said, this is kind of the silly problem. Nevertheless, it's the problem that that sort of like won't go away as the fun little example problem. So much so that there is a karate club. If you are the first person at a network science conference to use the karate club as an example in your talk, and if the little trophy, which you can barely see here in the blurry photo, happens to be there at that conference, then you would become inducted into the club. I am not in the club. There's a whole embittered multiple-part story about that, but that's okay. But it's an awesome little playful thing that we do. But let's try to be a little more serious than the karate club, and talk about some other ways in which this might be useful. So this hairball is a connected component of 762 Facebook users at Caltech back in the dark ages of Facebook. Back in its very early days when you actually needed a .edu address to even be on Facebook in the first place. And so every one of the nodes denoted here by different colors and symbols in this hairball, every one of the nodes here is a Facebook user at Caltech, and of course the edges between them are their Facebook reciprocated friendships between each other. And if it weren't for the fact that I had already colored and symboled the nodes here, you probably wouldn't see that there's a whole lot here. But there's sort of a green splotch over here, and there's a yellow splotch over here, and sort of a blue up here. Every one of these indicate the residential house affiliations of the user. So even in these early days of Facebook, it said on it, you could volunteer, where did you live? And so they were volunteering which one of the houses at Caltech that they were affiliated with. Houses at Caltech are maybe just to quickly explain, the residential housing system at Caltech is exceptionally heavily structured, and Mason Porter, who was part of this work, my longtime collaborator, had been an undergrad at Caltech, so he was helping drive some of our interest in this, because students come in and they go through this, almost rush-like, but it's not a Greek system, but an almost rush-like quick self-sorting into these houses, and then the vast majority of them stay in the same house all 4 years, and they actually live in the house, or they live in a building that's immediately associated with the house. And so the hypothesis here was that the large-scale structure of this network should surely reflect that underlying key piece of the social life of students at Caltech. But in this force-directed layout, it doesn't seem to be doing a lot other than, okay, well, yeah, like I said, there's a lot of green down here, and so the colors largely are grouped together. But if we go do community detection on this, so this is a representation of one particular way of doing community detection on this network, where now we've replaced each of the individual nodes with, we've just sort of piled them into pie charts with each other, each pie chart representing one of the communities that was identified, and then the wedges in the pie chart representing the number of users associated with each house. And the pie charts are different size because they're actually proportional in area to the number of users who got put in that group. And certainly here near the center of this network, you definitely see that these communities are very heavily associated with this residential house label. This group here is over 3/4 whatever this maroon house is. This one is over 3/4 the yellow house. This one's almost 3/4 the green house. These two dominant colors right here are actually two houses that are right next to each other on an end of campus that have a lot of social interaction between them. So that actually makes a lot of sense there, that they would in fact be grouped together. And indeed, what you see here is virtually every single color is heavily dominating one of these communities, except obviously which color? What's the outlier color here? Okay, so there's a little bit of blue. Well, those are those two different blues? Those might actually be two different blues there. These are the same blues. All right, so either this was like way too out of a rhetorical question, or you're all colorblind, or the projector is purple. Purple, I mean, that's what that color is, believe it or not. That's a purple. Whatever it looks like from where you're sitting, it's actually a purple on this projector, right? I mean, it's over here. It's like there's a big purple wedge in every single one of these. It's like over 1/4 of this community. It's these communities by themselves. What the heck is going on with the purple house? The purple house isn't a house. It's the people who didn't tell us where they lived. But so if you're putting together some sort of social event for Lloyd House, which I think is the yellow house here, but don't quote me, right? I'm probably sending an invite to everybody in that purple wedge, right? This is at least seems to be the distinct possibility that many of them, whether or not they either probably live in Lloyd House themselves, or they're so tied into the Lloyd House social structure that they might want to come to our event. So this was just sort of showing one demonstration. There's like way too many things that we could talk about when it comes to different ways that you can do community detection. So for the most part today, all I'm going to talk about is this notion of modularity. And the notion of modularity down here is simply, in words, that a good partition of your nodes into communities would be one for which you have a much larger within community edge weight, total edge weight, than you would expect at random. Sort of a beautifully phrased sentence, right? You have much more within group edge weight, and I use the words community, group, cluster, whatever, like interchangeably here. You have much more within community edge weight than you would expect at random. But sorry to be the mathematician about it, now that I've said at random, I have to say in what model. And that's really the whole point of this theoretical background for you, is that it does matter in what model. We're going to try to go through that. We're not going to try to cover all this other stuff, but we will give you some links. And then there are some review articles of different flavors and stripes down here. Some of it demonstrates quite how enormous this field is. Santo Fortunato has this now nearly 10-year-old physics reports review. If you look at the page numbers here, 75 to 174. And physics reports is like one of those like 2-column, really tiny font. Like, I mean, this thing's insane. It's a tome. We tried to write something that was a little more of a survey near the same amount of time, same period of time, and more recently, Santo has something that he calls more like a user guide, but it's still giant. Ours is this case studies paper. Jim, this is going to appear in a book someday, right? Okay, all right. So Jim asked me to write this for a book, and whatever. So it hopefully will appear. I have him on the spot right now, but it's available on the archive preprint server. So if you like literally type archive and those numbers in to Google, it'll find it for you. All right. So what's modularity? Let's try to mathematize. We won't spend a lot of time looking at formulas, but at least let's take this formula here, because this is just quantifying what we just said about it being the total edge weight minus what you would expect at random. So what that means is I'm going to sum over all pairs of nodes, I and j indexing my nodes. The prefactor doesn't really matter because we're going to optimize this thing anyway. Like, we're going to look for the maximum value. And the game is we're going to place the nodes into communities in such a way that we get the largest value Q. So the thing that we're going to sum over is some matrix with elements Bij, which we will call a modularity matrix. We'll come to that in a second. And this indicator, this is just sort of a fancy way of writing that whether or not the community Ci that I put node I in is the same as the community Cj that I put node j in. And if they're the same, then this delta becomes 1, and if they're different, then it's 0. So all we're doing is we're summing the Bij elements where I and j have been put in the same community. That's all that means. And so now what's Bij? Well, Bij is whatever your data is minus some random model. This is the spot right here where what do you mean by at random? And everything comes down to picking Pij in a way that respects your data. So if you get, I already said that if you get like only one thing out of this talk, it will be about resolution parameters. If you get a second thing out of this talk, it will be what kind of data you have might affect what kind of random model that you have. And so to be a good user of the existing codes, these are the two things you got to be looking out for: resolution parameters and what model. So, and then this is just like a lot of detail. Unfortunately, while there's a simple goal here, it's a simple formula, and the goal is simple to state that what you're going to try to do is assign nodes to these communities. That is, you're labeling the nodes with these community labels in order to get the biggest value of Q. This is a computationally complex problem that scales exponentially with the number of nodes in your system, effectively because the only way to guarantee that you have the right answer is to check a non-vanishing fraction of all of the possible exponentially many different collections of community labels. Luckily, there are a lot of good heuristics to do this. And so that's where the codes come in, is that there are heuristics we'll be able to lean on. So what about this P? So this is a little easier for this audience than maybe sometimes when I talk to sort of random graph model people in a math audience. Random graph people in a math setting, the first thing they want to say is, well, the simplest graph models are just, you say you have an Erdős-Rényi random graph, every edge is there, IID with probability P, and then you go home. But unfortunately, that's not a very good model for most real data. That's something that, you know, in the much more complex models that you end up with for social networks is maybe not surprising. One of the ways in which it's obviously not a good model is that if you assume that every edge is just there IID with probability P, then your degree distribution ends up being just a binomial, or in the limit of a large network, a large sparse network, it's effectively Poisson. So this inset right here, you can't read the numbers, that's okay, because the shape is very different. This inset here is what happens if I take a network of the same size as that Caltech Facebook network and the same overall density of edges, and I just randomly drop those edges into the network. What is my degree distribution look like? And it's very strongly peaked, right? It looks a lot like a bell curve. Central limit theorem comes in, and so it's very strongly peaked and at the mean degree. And the numbers here actually, you know, even I can't read them on this fuzzy projector, but they only vary from like 25 to 45 by a whole lot in there. In contrast, the main figure here is the true degree distribution of that data. That's much higher at very small degree. There are many nodes in this data that have very low degree, and it has a much longer tail than what you get here in the inset. So there's no way that a random graph model that's going to have a degree distribution like this can be a good fit to the real data that has a degree distribution like this. The degrees matter. Heterogeneity and the level of play, the level of interaction that a node has in the network is a very real part of this network. And so the dominant null model that's used, random model that's used, is something that was developed by Mark Newman and Michel Gervin. And it effectively uses the degrees. So Ki and Kj are the degrees of nodes I and J. Actually, I should also say if it's a weighted network, then you just put in strength here instead of degree. You do weighted degree. So Ki and Kj are the degrees of nodes I and J. W, again, is the total weight of all the edges in the system. And so your expected weight of a connection between I and J is simply this product divided by twice the total weight of the system. This is assuming you have an undirected network. It's assuming I'm not including any other structure other than this heterogeneous degree distribution. And then there's this funny gamma that we stick on it. It's not in the original Newman and Girvan definition of modularity, but was introduced later to account for some well-known problems with modularity having a resolution limit that will come back when we talk about, when we go through the demo. But effectively, the idea here on gamma is that if you make it very large and you think about how P shows up in the formula, since it's something I'm subtracting off, if I make gamma very large, then I'm putting a big penalty on putting nodes together in a group. And as such, it's more likely that my answer is going to be many more communities, all the communities being smaller. If gamma is really small, then I'm paying a smaller penalty. And so there's a greater chance that my final answer will be to have a fewer larger groups. But we'll play with that. And then, and so then again, I sort of mentioned, if you don't have this structure, maybe an Erdos-Renyi random graph wouldn't be so bad. But in practice, most real data, this is a terrible model. So we switch over to the Newman-Girvan model. But this was assuming that it's an undirected graph. If you have a directed graph, then you have to distinguish your in degrees and your out degrees. That was some work that Elizabeth liked and did with Mark de Newman. Similarly, if you have a bipartite graph, right? If all of your nodes, if you can color all your nodes red and blue such that all of the edges in your graph connect a red node to a blue node, like back in the original data when Jim talked about papers and authors, right? So the papers are one color, the authors are another color. The papers don't write each other. The authors, if we don't count email, don't write each other. But they certainly don't write each other into existence unless they're fictional authors. And but the authors write the papers, and so that's where the link is. And if you're going to keep the data at that bipartite level, not project it down onto something, then your random graph model has to respect this. And so here, Ki and Dj are the degrees of the papers and the authors in these examples. And if you try to connect two papers or you try to connect two authors, then by definition, there is no edge between them. And so your random model has to respect that underlying structure. This is just to say, by way of in practice, right, many times we'll just go grab, and in fact, in the notebook that we'll go through here at the end of this, we just blindly go through and call functions. If your data is not an undirected network, you might need to look at the documentation a little more closely just to make sure that you're calling the function in the right way to respect whether or not it's directed or bipartite or signed or what have you. And then just to talk a little bit about how these things actually get solved. One of the most popular methods that we will run in the notebook is called the Louvain method. If you have a better accent, I'm sure you pronounce it slightly differently than I do, which is fine. I can't pronounce my own last name correctly, so God help me with this. This is a beautiful paper by Blondel et al. My postdoc advisor used to somewhat sarcastically say that your paper only needed to have one really good idea in it because that's one more than most of the rest of the literature. But this paper's actually got two really good ideas in it. One of them is that they came up with this cute formula. We don't need to go through it or why it's important, but they came up with this cute formula for being able to very quickly calculate what's the difference in modularity if I take a node out of the community it's been placed in and I just hold it as an isolate by itself. And having an easy to compute, and this is basically just algebra, but it's very smart algebra because all these extra symbols that get picked up then basically become the things that you have to bookkeep in an efficient code. And if you know what those values are and you just update them as you go along, then you can calculate these delta Qs very quickly. And so you can figure out if I take this node out of this community It's by itself, what's the change? And then if I take that node and I put it in another community, what's the change? So you can compute these things very fast. And the second good idea is in this diagram here, which is basically what they do is they start with their network, and they start moving around one node at a time until they can't do any better. They can't improve modularity by moving one node at a time. And there is randomness here because there's the order in which you pick the nodes. So this is not going to solve the NP-complete problem. It's just a heuristic. But they move one node around until there are no other single node moves that improve modularity. And then they aggregate it all. So they take all the nodes here that are in the green community and they just make it a single green node. And they do that for the other communities here in this diagram. And now they move around the whole little group that they had as a unit until they can't do any better. And so in this little cartoon toy model here, I always forget which way it goes. I think the green and the red merge together and the two different blues merge together. And so now it just looks like that, and that ends up actually being the answer in this example. But by doing it in this way of going up the levels, it's actually a wonderfully fast calculation. And so it's one of the most popular methods that's used. All right, so why would you do this? Here's just I'm going to blow a couple references at you just to sort of argue why it might be useful to compute communities. One of them is back to this bit about the spread of information or of an infection that I mentioned before. So I love this paper by YY and his collaborators. And basically what they did is they studied the spread of memes on Twitter. And they identified that their machine learning classifier that they tried to put on this to try to predict from early data whether or not a particular meme would go viral or not depended a lot on whether or not the meme had already crossed a community boundary. Basically, the idea being that a meme that just sort of keeps going around the same group of users, if it isn't going to get out of that group of users, and it's never going to get a chance to go big, or it's less likely to get a chance to go big. But if it's already in an early stage started to hit other users outside that community in other groups, then it's more likely to go viral. That's real data. This is simulated data in some work that Sergey Melnik and James Gleason and Mason Porter and I did a number of years ago. Here what this is comparing some simulated SIS infections. Actually, I'm sorry, this picture is actually a Watts threshold model, but in the same paper we do SIS as well. So this is looking at the size over time of a Watts threshold cascade of simulated cascades on different empirical networks, comparing the simulated results with some differential equation models where it's basically like compartmental modeling of how quickly this is going to spread. And the differences here between the blue dashed line and the red dashed line is the red dashed line is sort of the state-of-the-art so-called heterogeneous mean field model for how quickly this cascade should spread through the network. But this heterogeneous mean field model only has information about the degree distribution in it. It doesn't have anything about the community structure. And if you include community structure as part of the calculation, then you get the blue curve and it's much better. In fact, if you only include the community structure information and you ignore the heterogeneities in degree, you get this dashed line, which already does a pretty darn good job and certainly is much better than the red one. So knowing about the communities helps you predict how quickly things spread through the networks. And in fact, this is related to modularity sort of after a fact. This is one of my favorite papers by Renaud Lambiot and some of his collaborators. That there should be this relationship is actually inherent in the definition of modularity itself. The argument I gave you before is sort of a counting argument definition, right? How many edges do we count minus what we would expect in some model? What Renaud and his collaborators did that is just sort of beautiful is they went back and they looked at random walkers on a graph. I mean, strictly speaking, for those who care about such notation, they looked at expected populations of random walkers on a graph, which is called Laplacian dynamics. It's basically diffusion on the graph. And as the random walkers diffuse on the graph, if you put down a bunch of community labels, you declare you have a bunch of communities, and you calculate a stability of those communities under this dynamic process. So specifically, if you calculate an autocorrelation for whether or not you stay in the same community relative to what happens at independence, at stationarity, then the formula you get for this stability is approximately modularity. It's kind of a beautiful thing with matrix exponentials and things that warm my linear algebra trained heart. But so it's a really neat idea, and it's that modularity is actually just an approximation to the stability of these communities under a dynamic process like this. Moreover, and here's kind of the cool part, since I just sort of threw that gamma up as an ad hoc thing, gamma actually shows up in their rederivation as an inverse timescale. So what I told you before was if gamma was really small, right, then that means we pay little penalty when we put nodes together. So we're more likely to end up with a few very large communities. And so if gamma is small, that means that the time of this dynamical process, the number of steps that you can take in the random walk, is very large. So maybe you've had a chance to move through a large part of the graph. And so you've gotten further. And so your notion of what a good community, a good stable community is going to be larger at small gamma, because that corresponds to larger times of random walking on the graph, than if gamma is very large, then that's very short time kinds of stuff. And so you can't get very far if you're just diffusing for a very short time. And so you're going to end up with many very small communities. And again, we'll see some of this in the notebook. And then just some descriptive things very quickly as other reasons why you might want to do this. And then we'll see what else we're going to do with the time we have left. So here is a purely data. Sometimes all you want to do is you want to just try to understand your data, right? You're just trying to explore your data and see what's in it. So this is an adjacency matrix. It's for a weighted network that is the similarity of roll call voting in the 85th Senate in the United States Congress. I think there's actually 101 senators. Somebody died or had a sex scandal or something. But what's being measured here on the heat map, which I have already sort of very deliberately reordered the senators in order so that the block structure is obvious. The more yellow-orange colors, those are senators who agreed with each other a lot of the fraction of times that they were both present and voted. The blues sort of off the diagonal here are people who didn't agree with each other a lot. I've already deliberately removed the diagonal just because the fact that you always agree with yourself is not terribly interesting. So you can do community detection on this, and perhaps unsurprising, you're going to identify that there's one group of senators over here, there's another group of senators over here. Maybe if you squint a little bit, you say, well, there's a smaller group of senators right in there. And in fact, you can identify these kinds of voting blocks in the Senate. Similarly, we've done some work where we looked at committee assignments in the Congress and looked at the ways that the committees are connected to each other by virtue of having, this is actually in the House of Representatives, not the Senate, but ways in which they're connected to each other by common memberships. In case you're wondering about changes in American history, the 85th Senate, if you're not used to this kind of data, this is 1957, 1958. It's the beginning of the civil rights era of legislation. It's a rather contentious time in American politics. Nevertheless, there was some cross-party agreement. This is what things look like today. It's my team, your team. This is being recorded. This was equal opportunity bashing both sides of the aisle. So I'm now in trouble with everybody. So yeah, that's kind of depressing, but it is what it is. And then Jim did this beautiful visualization, maybe just to lead into the fact that visualizations will get talked about, where what we've done is we've actually used the value of modularity that we were talking about as a measure of how polarized these senates are. So I guess I should, in this case, splitting this one into two groups is kind of easy, right? And it's, the network almost just falls apart in your hands into two groups here. There's so little voting agreement across this divide. Whereas clearly it takes a little more creativity to think about what the best way is to split this into two or into three groups. And effectively, modularity is measuring that after a fashion for you, right? By talking about how dense the connections are within the groups. I mean, here you almost only have connections within the groups. Whereas here, right, there are many more connections that go across the group. So this is going to be a lower modularity than this one. This is, in that sense, much more polarized in a roll call setting. And so what Jim did is he took some of this data that we did. He actually grouped senators not by modularity, but Jim, which method did you use again on this? I used to know. Right. Okay. So it's all structural equivalence, which is one of the other awesome ways to do things like this that we're not talking about today. But the neat part here is, so this is going in time. So this is a 2-year Congress at a time. And the neat part about doing it by structural equivalence is he ended up with a whole bunch of senators who didn't neatly get grouped into either the blue block or the red block, colors being obvious. So you get to sort of see this legislative middle, and that it kind of hollows out over time at the same time that the two nominal parties here not being labeled by whether they put a D or an R after their name, but by their actual true voting patterns, they get further and further apart from each other. So you can see the increasing polarization in the Senate and the hollowing out of the center at the same time. So I think, so all credit for the beautiful part of this goes to Jim. All right, so one more motivating example of why it's sometimes useful to look for these communities, blocks, groups, whatever you're going to call them in your data. True story, literally this picture, oops, I was showing it to a friend of mine. He happens to be an infectious disease specialist at Washington University in St. Louis. And he asked me, what if the senators were E. coli bacteria? It always gets a good laugh. Yeah, told you, at least 25% bad jokes. But so what if the senators were E. coli bacteria, and instead of voting on bills, they had similar genetic virulence factors, or the metabolomic signatures that patients had from them were similar, right? I mean, again, you can, as Jim said, you can turn everything into a network, and in my case, you can then do it as a graph partitioning problem. So every one of the nodes in this diagram is a culture from one of 337 UTI patients who presented at this clinic in St. Louis. And the edges between them, the very dense but weighted edges between them, is a measure of the similarity in their genetic virulence factors, looking at a very small handful of the sort of conventional wisdom in the literature heavily looked at genetic virulence factors. And I wouldn't be telling you this story if they didn't obviously group it well into communities. There's sort of a big red group, blue group. I've colored them as such here, just 4 communities we happen to find by way of doing this. The far more interesting thing to me here isn't that we found communities, it's what can you now say about the data because you've identified these communities. And what's really interesting about these communities is that they appear to be very closely related to host sex specificity and to antibiotic resistance. So over here are just a couple tables. I'm just grouping the 4 communities of what percentage of the patients here are male versus female, and you see that there's some large discrepancies between group 1 and group 2, the dashed line being the population average. Here's resistances to the 2 major antibiotics. So if someone presents in group 2, the red, and if you could classify their UTI as group 2, giving them Cipro is a bad idea, right? You want to give them Bactrim, not Cipro. And I mean, at least, on average, as an on average correlation, not causation, yada, 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 thing here, it seems to at least be leading that way. Whereas if they present from group 1, the black group here, then Cipro is great, or the green group, group 3, Cipro is also great. There's no observed resistance of Cipro, at least in the population in the green group here. So what we're actually working on actively with some funding from the NIH right now, the NIDDK specifically, is recapitulating these communities and these host sex specifications and antibiotic resistances at the level of metabolomics rather than genomics. Because the dirty secret of this awesome result is that it's sort of useless in practice right now, because the time, somebody presents in clinic and you culture their sample and you wait a few days for it to grow in the Petri dish, and then you send it off for genetic assessment, and then you do all this, and then you group them into one of the three things, and they have a raging UTI because you didn't give them an antibiotic when they presented in the clinic. So that's a bad idea, right? But if instead, just, the dream here is, not to be sort of too crass about it, but patient presents in the clinic, hi, go pee in a cup, please, and then go shove that in the mass spec machine. And if you can recapitulate this from that sample, then you could immediately have a clinical indicator for which antibiotic to prescribe. And then there's other things about that. Okay, phew, all right. So that was indeed supposed to be the longest part of the talk. Everyone pauses, they look at this. What time did the schedule say I go to? 3:15? All right, I'm on target. All right, so now that we've hopefully motivated you and you've decided that this is the greatest tool in your toolbox of all the tools you've learned about this week, how do you actually calculate any of these things? And when am I going to tell you more about these resolution parameters? So here's just a couple slides. You all have the slides. You can see them. I don't need to go on about them for too long, but some little pointers of cool software that you might want to know about. Gephi does beautiful visualizations. I don't know if you were going to talk about Gephi at all. A little bit. Okay, among other things, it has little drop-down boxes for finding communities and other little parts of those drop-down boxes that let you actually change resolution parameters. So that's good. So yay, Gephi. I should also say, oh yeah, and there's a whole section in the tutorial about community detection, so you can get that in there. I should also, despite the fact that this talk, because my own research is very modularity heavy in terms of the tools that we use, I should say that this makes me sort of heretical in much of the community detection literature, and I don't play well with all of my friends anymore, I guess, because I'm still trying to do things with modularity, but a lot of the community and network science has moved on to doing everything by stochastic block models. I've also done some things with stochastic block models. If you are interested in fitting stochastic block models to your data, GraphTool is really this just tremendously amazing block of software. It has lots of different options for different kinds of stochastic block models. I highly recommend you check it out. And here's just me showing their sort of inferring modular network structure section. So it's all in a generative model framework where you actually have a model for the network and you're trying to infer the parameters of that model, as opposed to modularity is a very descriptive framework, right? It's just an objective function. You're finding community labels that give you the largest value. And then here's a third completely different kind of method. It's mapequation.org. It's also sometimes called InfoMap. It's an information theoretic idea. It's all about coding lengths and about a good community is one for which you would be able to use the communities as labels of a random walker in order to have a very efficient code for describing the paths of those random walkers. It has some beautiful code that are associated with it as well. So other good things to play with. We're not going to have time to talk a lot about multi-layer community detection. If you have an interest in multi-layer network data and you want to talk about that some more, you can always find me. I'm always happy to talk about these things. GenLouvain is sort of a generalized version of the Louvain algorithm. It strips out one of the good ideas of the two good ideas that I said was in the Louvain idea, and it sort of leverages only one of them, but in a way that lets you put any random model that you want to compare against your data, and so it's very flexible for doing very general multi-layer network structures. And so you can find GenLouvain here, and again, I'm happy to talk about that. And then finally, something that will come up at the end of the notebook is there's a new method called Leiden from Vincent Trog and some of his collaborators, and there is a Leiden alg package in Python. It's purportedly better than Louvain, faster, and typically gives better results under many different settings, and so this is a brand new Python package that he has, and importantly, there is a way to call it from R, which we'll show you at the end, and that will probably work on nobody's computer in the room except for mine. So just because unless you've already done lots of things, but we'll tell you how to do this. And then last but not least, or at least I think this is last of the software pieces, CHAMP. So CHAMP is a method after that we won't unfortunately have a chance to really talk about today, but we've talked a lot about the importance of resolution parameters, and we'll see more of that in the demo, but we're not going to be able to say a lot about how you pick the resolution parameters. We'll tell you a few things about it by way of some examples in the notebook, but if you really want to go deep on trying to reconcile what resolution parameter you should be running some things at, this Python package from my students Ryan and William is really the way to do it. But we'll maybe show you a little bit of the theory of that. And then of course, what we're going to do a lot of, because we're here, is R and iGraph. And so we'll at least show you how to do things in R and iGraph. I should say, as maybe an advertisement for one of my favorite books, because I just taught a bunch of first-year undergrads with no prerequisites out of part of this book this last spring, Statistical Analysis of Network Data with R by Eric Kalakshik and Gabor Shardi. So I really don't get any royalties by advertising someone else's book. Is a fun little sort of step-by-step tutorial on how to do a lot of different things in R. So I recommend it, particularly if whatever institution you're at has a good Springer Link subscription. You can probably just download the PDF of the book from your library, which is always a win. So I recommend that because it's all built in R iGraph. All right, so finally, a few things about the resolution parameters. We'll say at least one or two things about it, multi-layer networks, and then we'll go to the notebook. So we have our formula, and I'm going to rewrite our formula for modularity to make the gamma explicit here. And I'm sort of going to just collapse a lot of terms as details. So again, here's our modularity matrix. In the parentheses, Aij is your data. I'm just taking whatever the Pij was because of my whole soapbox about directed or undirected or bipartite or what have you. Let's just assume you've got a model there, it's Pij, but that it has a gamma as part of it that's multiplying it. And so you want to pick the labels. So here I've written Ci, and I'm using sigma as the solution that you have, the set of the partition, the set of community labels. And so this is the community label of node I in partition sigma, the community label of node J in partition sigma. If they're the same, then you include this term in the sum. I'm ignoring the prefactor because I could have just absorbed that into somewhere. And we're going to just sort of, gamma's like kind of like the knob. One way to think about this, and sort of what we'll do in the notebook, is gamma's sort of like the knob on your old analog radio. I'm old enough that my first car only had an AM radio, right? So you'd sort of like tune it, and the signal would be weaker, but then it would sort of in a band, it would be really strong in the center, but you'd kind of be able, if you didn't quite hit it right, then you could still hear it. And in one way, that the kind of notion that a strong signal was robust to my tuning the knob is something you might expect to happen if you had a strong community structure. So here's just a particular example. Ignore all the curves for now except for the dark magenta one, because that's sort of the main piece of the story here. And what we're plotting here is up to some rescaling by the number of nodes in the network, how many communities have I found by running a heuristic at different values of gamma. And what we see here in this sort of highlighted gray region is a nice wide plateau of this number of communities that we found. There's lots of other diagnostics in here that then indicate whether or not they're actually the same communities or not. But basically, this is the spot where, for this particular data set, this range of gamma, which is noticeably not the default of 1, this range of gamma seems to be giving us some relatively robust answer. So this is letting the data tell me how many communities it should be partitioned up into. And so having a plateau like that is a strong indicator that that's real. Whereas if I just sort of pick the value 1.2 at random, this is just sort of jumping between some structures that might not have anything to do with the real signal here. We can certainly do more than that, though. We're going to take that a little bit further with this CHAMP idea. And then again, this is just the link to that CHAMP code, which was a paper from a couple summers ago. But I should note that there are some other important works that are complementary to this for picking resolution parameters in the literature. But here's basically the idea. The idea is, all right, let's try to just kind of do this again. And we're going to do this here on a particular data set. This is an old college football data set. Every team here is a college football team from the 2000 season in what was then called Division 1A. And there's a link between them if they played a game that season. And because if you know anything about college football, there's very strong conference and then inside most of the big conferences, division structure to football, we end up with sort of big clusters that represent the conferences in college football. And so this is a well-clustered data set. So what we're going to plot here is we're going to plot in the orange the number of communities that we've got at different values of gamma, and we're just going to randomly pick the gamma, and we're going to go completely overboard and do this 50,000 times and show you how many communities do you get reading off of the right side here at the different value of gamma. And if you do that, well, you know, there's maybe a plateau here. It's not as clean looking as on the previous example, which was a very strong structure. But the fact that this is such a well-clustered data set and sort of only gives us a signal like this when we run it many times is a sign that we need to do a little better. And doing a little better is mathematically driven by recognizing that when we take that rewritten formula for modularity, we just yank the gamma out, everything's just a linear function in gamma. Everything else, once I pick community labels, this is just my data summing over the cases where the community labels are the same, so that just gives me some value A hat for that set of community labels. Everything here similarly just sums over, given that my Pij is some null model, so it's a P hat. And so whereas in this figure here, we've plotted, in addition to the number of communities we plotted the value of modularity, not renormalized. I didn't stick the scale factor in front of it. And you can see how it just gives you different points, and those points sort of fill out an envelope. If I don't plot these just at the value of gamma that I stuck into the code, but I plot it for all values of gamma, so I get a set of community labels out, that set of community labels, sigma, just defines a line. It's a line of Q versus gamma. And so instead of it just being a point here, every one of my possible solutions is a line. And the neat idea of this code that I encourage you, if you get interested in this, to go look at, you don't have to worry about all this because the code does all this under the hood, right? Is now the game becomes find the spots where you're on this upper envelope, what's the largest value of modularity that you can get as a function of gamma over all the different answers that you generated by calling the code many times. So in this example, we happened to call Louvain 50,000 times. It only actually gave us 384 unique answers, which is already a big win over 50,000, right? But 384, looking at 384 different answers at the same time is a lot to look at. But it turns out that only 19 of them ever live on this upper envelope here. So the other 300, and I'm the mathematician, I should be able to do arithmetic, right? The other 365 are all subdominant. None of them ever win. And so why are we looking at them? They're just artifacts of the fact that we ran a computational heuristic. So the cool part about this code, the CHAMP code that I'll stop advertising and move on for other things, is that it lets you run this many, many times as long as you're running things at different resolution parameters. And then it helps you sort of reconcile your results. Okay, maybe I'm going to skip I think, some of the rest of the slides. You've got them. There's just lots of cool things about multi-layer networks, and maybe I'll show you one thing about a multi-layer network. Sort of say just like what it is, and then we'll go to the R notebook. So everything I've talked about so far and that we'll do in the R notebook are just regular networks, but I think it's useful to also say something about multi-layer networks since that's where a lot of the literature is right now in this space. And all we really mean by a multi-layer network is a situation where you have many different kinds of connections. It might actually be multiplex data, where you have people who are friends, people who are family, people who go to church together, people who go to school together, and you're keeping track of the differences in those ties. It could be temporal data, right? It could be different waves of data, like in the Senate example, right? We might have 1 year and then another year and then a third year. There are some crazy things people do with multi-layer networks to try to describe things going on with infrastructure. Because like you have energy grids and road networks and subway networks, and they all have to interact with each other, and the ways that these different networks are networked together. So a multi-layer network is just a catch-all framework for any of these kinds of things. And so if you do that, then the trick becomes, if you have some data structure that has a much more complicated way in which the networks are interacting with each other, you need to respect that if you're going to do community detection on it. Just like if you know your underlying data is bipartite, you want to respect that. If you know your underlying data is a multi-layer network with different properties in the different layers, then that's something you want to build into your random null model in multi-layer modularity. And that's where the Jen-Louvain code that I showed the link to before can be very useful. So again, that's all an invite to say, if you have a multi-layer network problem and you want to learn how to do community detection on it, I'm happy to help with that. But in the interests of us not running too much further over time, I'm going to skip all of the rest of that part of the slideshow, though you can see lots of references in there. And instead, I want to just jump to, let's see if we can get this to, okay. I just want to jump to the R notebook. So in the Dropbox folder, there's an RMD file that you can pull up if you want, because then you can just cut and paste code, or you can just follow along with the HTML file, which is just the output to sort of see the literate computing narrative here of how these things work in practice in R. Again, I've sort of, for completeness for you, listed these four review articles again, and also Eric and Gabor's statistical analysis of network data with R, since a lot of my just learning how to do this for my students this last year, because R is not my native programming language. I live, breathe, eat, and sleep MATLAB. But it's embarrassing. I dream in MATLAB occasionally. It's always a, yeah. But not in R. And so, so I owe a great debt to them for showing me how to do this just in time before some of my students. So we're gonna have fun with the Zachary Karate Club for the purposes of this, just because we talked about it already and you can see it play out. Of course, you have your own network and you might want to see how some of these commands work. In order to pull up the Zachary Karate Club, I think you need to have the iGraph data library, which might not already be installed. That's a package that would install blindingly fast. Install.packages, iGraph data, just like, or Dana, did you say it's in the core install that you've now copied it in there? So everything should be in Dropbox. Okay, so if you have iGraph data, then the data karate command should pull up the Karate Club as a data object. So who wants to, did anybody pull up the data object? Yeah, all right, one person's willing to admit she pulled it up. Good, I've got one person trying to do things. All right, a second person trying to do things live. Again, you don't have to do it live. What does the data look like? Well, the data is 34. It's an undirected weighted graph, 34 nodes, 78 edges. It's got a title on it. There's all these great attributes about the data. The one that's most interesting to us for the purposes of the narrative about Zachary's Karate Club is faction. That's the two subgroups that things break up into at the end. And then, of course, here's just a big list of the different actors and the edges between them. And so that goes on for too long. We'll just jump to the pretty picture. So if we plot this, then what you have here is you have the lead instructor and the club president. You can see are very much the hubs of these two factions, and here the color codes are by those factions, the clubs that they're going to split up into. We're going to see variants of that picture over and over and over again. So Louvain is easy to run because it's built right into iGraph. Again, though the problem is it's built into iGraph without any resolution parameter, which, again, if you take only one thing away from this talk, right, it's that resolution parameters matter. So this is somewhat frustrating to me that the resolution parameters are not in iGraph inside of R. And I don't really understand why they're not, since they are inside of iGraph in Python. But there you have, and we will have two workarounds for you by the end. So the cluster Louvain package, and your mileage, I should say, also might vary. If you go look at the Kalakshik and Shardy book that I mentioned, since it's from 2014 now, a lot of the function names in iGraph over the years have changed. Luckily, they're usually backwards compatible, so some of the old names still work. So things that some, there's like at least 2 different names of this function at this point, but I'm just going to use cluster Louvain here. And so we're going to run cluster Louvain and pipe the output to just a simple variable called KC for karate communities. If you don't like my naming conventions, you should at least be happy that this is above average for me in clarifying what the names of my variables are. My former postdoc, who had, before going to graduate school, been a professional coder for IBM for a while, she just used to tear her hair out. I mean, she'd be like, seriously, your code has this variable called it, and then later on, there's an it too. I'm terrible, right? So that's why it's important that the champ code was not written by me. It was written by William and Ryan in my group, not by me. So Jen Louvain, parts of that I can take blame for. So anyway, so KC will be our community labels that we got from cluster Louvain right here. The way that it comes out, the length is the number of communities, sizes tells you the sizes of those communities. And then you can use the membership function on this to see the labels. So unfortunately, the way that this wrapped, right, this is Mr. High is 2, actor 2 is 2, actor 3 is 3, wraps around, actor 15 is 4 in community 4, actor 16 is in community 4. So you have all the community labels that were found by the Louvain function, and you have the modularity value here, 0.445 rounding. I should say at this point that a common question is, what's a good value of modularity? And there are terrible things written in the literature. 6 minutes? Oh, 0.6. 0.6 is a good. Okay, so now that he's jumped into that, I will say anyone who claims to you that there is such a thing as a good value of modularity is wrong. There is no such thing as a good value of modularity that is good in all contexts. What the value of modularity might turn out to be can be very dependent on the size of your graph, the density of your graph, yada, 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 right? I mean, how do you assess the statistical significance of this? Probably you want to go do some permutation testing or things like that, or consider it relative to a bunch of random graphs generated. But there are these terrible things that persist in the literature that say things like, Mark Newman said that a value of modularity of 0.3 or better is good, and he never said any such thing. And it's like one of those telephone games. If you track back the literature, right, you can see how he said, well, in the cases here that we're looking at, it seems like 0.3 is a reasonable value, and then somebody misquotes it as a little stronger and a little stronger and a little stronger until it's now being quoted as this thing that he never said. So, so whether or not that's high or not is not going to be assessed right here, but it's certainly higher than any other value that we can get. And again, as hopefully has come through in my talking about the different examples, I'm far more interested in the stories that you can tell with these communities. So what do the communities tell you about the data? And again, in this case, the communities are telling you about these factions, as they're called here. And then the plot function in iGraph can take in communities nicely and make pretty pictures with them like this. So now everything's force-directed layout. And the colors are all the communities, and it's grouped around sort of these little clouds around the different communities. You can see that the force-directed layout and the communities don't sort of like perfectly align with each other in all cases. 10 being over here, node 10 will show up again a couple other times in this notebook. In case I need it later, because I gave it such a bad variable name and because I cut and pasted a lot to make this notebook, I'll now call this KC Louvain. So it's actually telling me what I got it from. That's one of the most popular methods. The next couple of pictures are just doing this now with some other things. Fast greedy is an old method by Aaron Clausette, and Aaron, well, for one thing, Aaron doesn't even like modularity anymore. So he's not going to tell you to use his old code because he doesn't even think you should be doing anything with modularity. But nevertheless, since it's built into iGraph, it's one that commonly gets run, much to his dismay. Here it happened to find 3 communities and a slightly smaller value of modularity than 0.434 than Louvain found. It's a very, well, I was going to say it's a very fast and greedy method. That's why it's called the fast greedy. It basically only agglomerates things. And once nodes are agglomerated into a community together, it doesn't give you any opportunity to split them up. And so it's faster than Louvain, but it usually doesn't do as well. One of the advantages of using it, though, and if you don't have the ape library already installed, then this next piece might not work. But I only use the ape library for plotting some dendrograms, is that because of the way that the greedy package only puts things together, it's a hierarchical set of communities that it creates. And so it can be directly visualized as a dendrogram, right, where the way to read this is at this end, you have the whole network. It splits into 2 groups. If you follow where the divide is, the 2 groups are right down here. It actually aligns perfectly with the split into the factions, which I haven't shown. And then you can see the further splits of it up. So sometimes you can use this hierarchical structure in place of a resolution parameter to see the split. The maximum modularity one, though, is the split into 3 groups, which happens at this point right here before that split happens. And so you can see the green is all there, separated from the blue. And then walk trap is just another common method. So I just sort of ran that. It had a slightly smaller value of modularity than Louvain gave us. Another pretty picture that goes with it. It happens to be a hierarchical structure, so you can see it. And then sort of here's maybe part of my trying to summarize quickly. Part of maybe a take home, even in this very simple case here, right? I mean, this is the karate club. This is like the simplest community, right? This is the one Eric said, if your method doesn't work on this, go home. So we've now run these 3 different methods, and we have 3 different answers, right? We have the fast greedy gave us 3 communities with this modularity. Walk trap gave us 4 communities with this modularity. Louvain gave us 4 communities with this modularity. And again, these are all trying to do the same problem, right? These are all only defining communities as a modularity maximization framework. Forget those like 20 other methods of doing communities that are in the review articles that I'm not talking about today. How are we going to compare these answers? What about the assignments, right? If we just start printing out assignments, right, we just get long strings of 1s, 2s, and 3s, and 1s, 2s, 3s, and 4s, right? And you can stare at these things for long periods of time, and that's not a productive use of your time. So instead of looking at a bunch of unwieldy lists of labels, what you can do is you can just make contingency tables. And you just pairwise directly compare the labels that you got from Louvain with the labels that you got from Walk Trap, or any other pairwise comparison that you want to do here. So here I'm just making a table of the Louvain membership, the memberships that we got from running Louvain versus the memberships that we got by running Fast Greedy. And so because we had 4 communities in Louvain and we have 3 communities from Fast Greedy, right, we're just tabulating how many nodes were in community indexed by row in Louvain versus community indexed as the column here by Greedy. And so we have 5 nodes that were in group 1 in Louvain that are in group 3 in Fast Greedy. And that immediately highlights for you that of course, nothing in anything we did with these group labels mattered which one we called 1 and which one we called 2, or which one we called gold, or which one we called silver, right? They're just labels. And the only spots we used the labels was to query whether or not two communities had the same label or not. So the fact that community 3 in Fast Greedy is identical to community 1 in Louvain is a perfect match. It's just, we just swapped the labels, right? So keep that in mind. And once you're keeping that in mind, you can see what happened here. Well, communities 2 in both sets are identical, and they have 11 nodes in them. And then community 1 in Fast Greedy got split up into what became community 3 and community 4 in Louvain. So that's the difference between the 3 community answer we had there and the 4 community answer. And now when we look at Walk Trap versus Louvain, Walk Trap's 3 is identical to Louvain's 1. Walk Trap 2 is identical to Louvain 1. Walk Trap 1 is almost identical to Louvain 4, and Walk Trap 4 is almost identical to Louvain 3, except for one little annoying node that got misplaced. And if you remember the force-directed layouts, that node happens to be node 10, that sometimes goes in different places. But what you really care about on any of these is not so much comparing them with each other as comparing them with the underlying data in the faction, right? Like, yes, I love to compute community structures, but what I love more is to do something with them. And so even though this is a well done by many times at this point, what we're doing here in the run of code that doesn't all fit with the diagram at the same time is, you can see what I'm going to do is I'm going to add shapes to my layout where all of the nodes in faction 1 are circles and all the nodes in faction 2 are rectangles. So now I'm overlaying the detected communities from Louvain, which I think was my old KC, or no, that's, well, at that point that I'm there, maybe KC is the Walk Trap. Oops. I'm overlaying all of those with this faction information, so we can directly compare. At least in this diagram here, it looks like all the circles are in these 2 communities, and all the squares or rectangles are in this community. All right, and as much as I liked that, I'm now going to get rid of that. So here is when you can just compare the table directly against each other. What are the memberships in Louvain versus what are the factions that were in the data? And so you can see the communities 1 and 2 in Louvain are the first faction, communities 3 and 4 are the second faction. All right, how much more time do I get, Jim? Okay, question. Yes, this is our markdown. That's why it's an RMD file. Yeah, sorry about that. So, oh, good. Okay. All right, so 10 minutes. Okay, we can do that. All right, yes, other question? Yeah, if I interpret your question, it's sort of what you're asking about is called consensus clustering, effectively. I mean, there's many different methods of taking multiple different answers and asking about the consensus between them. And that's a very common thing that gets done too.
Is it inbuilt in iGraph? If you remember?
That's a good question. I don't know the answer to that. That's, I don't know of one that's built into iGraph. That's a really good question. So, all right, couple highlights that are left in here, which is that first, I showed you lots of heuristics, and they gave different answers. And if they're all just optimizing modularity, why do they give different answers? Well, as we talked about before already, these are just heuristics for doing something that's a computationally complex problem that scales exponentially with system size. But luckily, the Karate Club network is small enough that you can use what's called cluster optimal in iGraph to actually map it. Basically, it maps it to an integer programming problem and then manages to check all the possible answers. So what you can actually confirm by running cluster optimal is like the right answer assuming that what you're looking for is to maximize modularity, which again itself might not always be what you want to do. And so this whole section of the document is merely seeing that if you do that, you just recover exactly what we got from Louvain in this case, which is certainly not always going to happen. So here's the contingency table of the memberships of Louvain going down the rows, and the true optimum going across the columns, and up to just community label swaps, you can see that they're identical. We're going to skip the deleting edge attributes section, but it's kind of relevant just because it highlights the fact that this Karate Club data is weighted, and that sometimes people study the unweighted version of it, so you can see what happens. I want to do just 2 more quick things by skipping down through that whole section. So I want to talk for 3 or 4 minutes about resolution parameters, and then maybe for 2 minutes about Leiden. So here's just a bunch of references I gave you in the slides. Again, I belabored that resolution parameters were important, and there have been no resolution parameters in this markdown file because there are no resolution parameters in our iGraph, and it pains me. There is no implementation that I know of native to R for this kind of resolution parameter for modularity, those gammas, which is just a total pain. However, there's this really cool idea from Alex Arenas and some of his collaborators. I like little bad jokes, so we promise some of those. I call Alex Spanish Peter because we both sport the same awesome haircut. And we're very confusing to people because we've had this run where we both get invited to be speakers at workshops together back to back. And it really confuses the audience. They don't know what, which one are you? You know, it's just kind of fun. So he calls me American Alex, and he's Spanish Peter. But anyhow, that's more entertaining to me than it is to you. But if you ever meet Alex, you're going to think you met him before. So, he and his collaborators had this awesome idea, which goes back to that random walk thing I told you about. And what they did is, instead of this gamma just tossed in, they just added a bunch of self-loop weights to their network. So if you just tag on big self-loop weights to every single node on your network, and you think about that random walk story I told you, then lots of times you're just going to stay in place, and you're not going to go as far. And they even considered negative self-loop weights as kind of like driving you like, wow, I can't hop out of here fast enough, right? And move on. And so they use these self-loop weights to modify the resolutions. And so that's what happens in this section of the document for you, is we basically take this data and we attach self-loops of different weight, and we see that as we increase, we'll just show the pictures. So this is the picture we had before. And as we increase the self-loop weight from 0 to 2, well, at 2, that pesky node 10 that was causing us trouble sort of pops out and becomes its own community. As we keep adding self-loop weights, and so now we're going to make the self-loop weight 3.5, you can see a few of the other nodes start to pop off as separate communities. This pair pops off together. And as you keep making the self-loop weight bigger, you keep breaking it up into a larger number of smaller communities. And because of the nature of the structure here, lots of those smaller communities are just singletons or pairs that come flying off. And so we just have a sequence of pictures that look pretty until finally you make the self-loop weight big enough that all you get is every node is a community unto itself. And you can do a big loop, looping over these results from different self-loop edge weights. And if you do that, so this is a plot here on log scale of the number of communities that we found versus the self-loop weight. And for a large range, or a large log range at least, of the self-loop weight, we just get the 4 communities that we had, and then it sort of increases. And do you see signal in this or not? I don't know, maybe not. It's only a 34 node network. So, it's kind of hard for there to be more than 4 communities. I mean, is this a real signal, a real plateau right here, or somewhere around 14 or 15 communities? Yeah, I don't know. You'd have to go in, probe what those are, but at least now it's letting the data tell you where some of the signal is and try to see it. We also run this on an Enron email example, but we won't talk about that. Here, maybe it's a little more, except for to say that if we look at the same kind of picture, here's one scale. maybe here there's another scale of something that's interesting. And so it would be interesting to go see what are the communities near these values of the self-loop weight. And then finally, the last victory that will definitely not run on your computer currently. But if this is something you care about, then I highly encourage you to go look at this. Those gammas, which are due to Reichardt and Bornholdt, so that's why I'm labeling them here. I didn't lie to you. There is no way that I know of native to R to do this. I'm a mathematician. I'm very precise when I say things like this, right? However, there is this really cool Leiden package from a guy named Tom Kelly, which is basically uses the reticulate package to basically just be a wrapper that calls Python and calls this new Leiden alg package in Python. So in order for this to work on your computer, anything from this part of the document down, right, you have to go to Tom Kelly's webpage right here and follow the instructions. And you have to have igraph and Leiden alg installed in your Python on your computer because all R is going to do is call Python. And obviously, if it calls it and it doesn't work, then that's not going to work. So, and that basically this lets you do the same thing. And I'll just stop with a couple of quick pictures, which is to say, unsurprisingly, as we ramp up the resolution parameter, we would get a larger number of smaller communities, but now we can also make the resolution parameter smaller. So here I happen to make it 0.6, and we get the nice clean split into the two factions. And we can do a loop, just like we had before. And so again, now the game is, how many communities do you get as you vary gamma? You can see that you can kind of argue, are there 2 communities, 3 communities, 4 communities, 5 communities? Each of these, because they just kind of nest neatly into each other, they all have some nice signal to them. And then again, we're seeing a similar plateau to what we saw before, somewhere around 11 or 12 communities. So if this is something that you're interested in pursuing, at a minimum, I beg you to do that self-loop trick, just to check that the answers that you're getting when you're running them in R are reasonable under increasing the self-loops. If you really want to be gung-ho, then you can use this trick as long as you play with some installations with Python on your system.